Welcome to Frank Stajano Explains and to the Algorithms course at the University of Cambridge. In this video, we are going to investigate Mergesort. If you're one of my Cambridge students, you've already been exposed to Mergesort in the Foundations of Computer Science course that you took last term. But that very elegant functional programming presentation hides some low-level details you must be aware of. In particular, all the sorting algorithms we have seen so far were capable of sorting the received array in place, whereas Mergesort typically requires additional workspace proportional to the size of the array it receives. So this is a point you must take into account when you decide which of several optimal time complexity sorting algorithms is best suited to solve your particular problem. So the next thing we look at, again, is something that you've seen in the Foundations course, but what you've seen in the Foundations course for Mergesort is a functional programming view of the world where many things that happen in the machine are hidden from you. So now in this algorithms course, because we are trying to cost how much things take, you have to take a lower level view and you have to deform the situation from things that higher level languages provide for free for your convenience. So what actually happens in the computer in memory in a case like Mergesort? Well, Mergesort is a program that sorts the array using one of your computer science superpowers. So you say, well, I'm given this thing to sort. It's long, it's big, it's ugly. What I could do is I could sort a smaller thing. And if I could sort the smaller thing and this other smaller thing, then I could just merge the sorted results. And that's a lot easier than sorting because the two individual things are already sorted. And by merging, I just take the smaller from the side that has the smaller item. I take that, and I keep taking the smaller from two sides. And that's all very nice. And how do I sort the smaller part? Well, that's the magic of recursion. Someone does it for me because it's smaller. Wait a minute, how do you do it? Well, if I have the smaller thing, I just split it into two, and then this one is sorted, and this one is sorted, and then I merge it. But how did you sort the smaller ones? Well, I take it into two, and I get to a point where it's just a one-element thing, and that's already sorted, so that's where I stop. And from then on, I just do merges. All right, so if I were to merge sort this thing, then the magic of recursion sorts this first four numbers for me, and so magic of recursion puts them in here like this. The magic of recursion sorts this other one for me in some other temporary space. And then what I need to do is merge them. And the way I merge them is I look at these two, and I can only take things from the left end and say, who has the smaller number at the left end? Well, it's clearly this one, so that's where I take it from. And who has the smaller between these two? It's this one. And who has the smaller between these two? It's this one. Who has the smaller between these two? It's this one. Who has the smaller between these two? It's this one. Who has the smaller is this one, and the smaller is this one and this one. That's all very nice. Except my stuff has ended up here. Well, maybe I should have sent it back there. The one thing you notice is different from what we did earlier is that I was dealing with my sorting in place, and now it's not in place. I've used lots of temporary space. In fact, I've been extremely wasteful of temporary space. But even if I am more careful, I do need to use some temporary space, because if I jumble this up again, somehow, even if I say, well, the magic of recursion, let me just define. Shazam will merge sort in place. So this thing will be merge sorted in place by recursion. How's it done? I don't care, it's recursion. Recursion does it for me. All right, let's pretend I believe you. But then how are you going to merge sort these two things? So if merge sort has sorted this, then in place, then it will look like this 3, 5, 7, 9. And this one merge sorted in place will be like this. All right, now you show me how you're going to merge sort these things. Well, I take the smallest of these, it's this one. And now you have to put it here, but here you still need to remember the 3 for later, so you can't really do it. You really need to use some spare space here for this. So you need to do this, and then this, and then this, and then this. And then at the end you can copy back there. So you are using some temporary space. Well, actually, if I forgot where these things came from, but let's stick them somewhere. If I am very careful, I can use less temporary space than the whole of this array. So I could use just half of this array and still get away with it relatively easily. If I say, okay, let me just have half of this as temporary space. Let me stick those things in here. Then I can leave those ones in here because as I take things into the final position, I'm freeing up space over here. So this one comes here, this one comes here, makes space for another one. This one comes here, this one comes here, makes more space. This one goes here, like this. So I can use just half the space. It's okay, but I still need to use some space. Well, actually, that's not true. There's some theoretical computer scientists have proved, in a paper interestingly named practical in-place merge sort. Practical, when you hear theoretical computer scientists talking about practical, that's a different semantics for the world than the one that ordinary people use. But anyway, they've demonstrated being able to do that with a constant amount of spare space as opposed to one that linearly grows with the size of the array. But we are not going to look at that in this course. So another interesting thing is that you are able to do merge sort without invoking the superpower of recursion. So if you have a messed up array again, what you could always do is start from the bottom up instead of top down. So if you start bottom up, you say, well, here's an array, and I'm just going to sort pairs of numbers. So 3 and 5, they are already sorted. OK, that's good. 9 and 12, they're already sorted. That's good. 7 and 4, they're not sorted, so they should be like this. 2 and 8, they're already sorted. Great. So now I have pairs of sorted numbers. So what I can do is now merge. So I consider this one, and I merge them. So the 3 or the 9, I take the 3. The 5 or the 9, I take the 5. The 9, well, now it's run out, so I just take this. 4 or the 7, I take the 4. Sorry, 4, 7, or 2, 8. Do I take the 4 or the 2? I take the 2. And then here, 4 or the 8, I take the 4. And then I take this, and I take this. And now I have a run of 4 that's sorted, and a run of 4 that's sorted. And so I merge sort these ones. Do I take the 3 or the 2? I take the 2. And then out of the 3 and the 4, I take the 3, and so on. And so I can do successive passes of merging larger and larger things without having to invoke any recursion, so long as I keep track of the size of my chunks and what happens when the size is not exactly a power of 2. I made myself an easy case here. So in your handout, I have been somewhat devious, as is in my nature, and I have not given you a working merge sort. I've given you a broken merge sort. Where is it? On page 33, there is a listing. It may look respectable, but actually it's a piece of junk. It's a piece of junk on purpose, so that you don't just read my notes on autopilot. You have to say, this part is suspicious. This part is total bullshit. And why? And you have to understand why and what needs to be done to fix it. There are a number of suspicious things, and there are a couple of exercises in the handout that you would do well to actually look at carefully, which try and make you figure out why this is suspicious and why you shouldn't trust code like this if someone else shows it to you, and why you should not write code where, for example, in one line, we return the same array we received from the caller. So I receive A, and I return A. While in another line, we return a new array created within the merge sort subroutine. So at some point, I make a new empty array of size len A, and I return this. So the fact that I do these two rather different things is an asymmetry that you should immediately consider suspicious. This is a signal that probably something's wrong. Why? Well, I'll leave you to figure this one out. And this other thing also to look at is if you do write your own merge sort, which I recommend, then you will encounter an issue with this part of the program. I mean, the sorting is easy. It's the merging that's the actual core of this. The sorting is done by recursion. And the merging has a subtle issue, which you should look at. Costing out the merge sort. So merge sort, we work through an algorithm that works recursively, takes an array, splits it in half, and applies itself recursively to each of the two halves, and then merges the content by taking the smallest element from each of the merged parts and sticking that into something that will eventually be the sorted array for everything. And how much does this operation cost? I don't know, but if I call f of n the cost of doing it on n items, this would be n items, and this would be n half items, then if f of n is the cost of doing it on n items, then this cost is going to be the cost of doing it on half the items 2 times, plus the cost of merging these together. And the cost of merging these together consists of taking something from here, or from here, from here, from here, and copying it. And I visit every element of the array once, doing a small number of easy operations. So it's going to be something that is linear in the number of elements I have. I don't care what this constant is, but it's something linear in that. And this is an equation that describes the cost, which is not very useful to me at this stage, because I have the function both on the left side and on the right side. And I would really like to have something where the function is on the left side, and then there's an expression that does not depend on f on the right side, so I can evaluate how much it is. So this is known technically as recurrence. And to solve it, there's a variety of methods. Your book has a chapter on tricks to solve recurrences. There's no recipe that works all the time, but there's tricks that work most of the time. And we are going to simplify things even further. And what we do is we usually try and guess. Okay, I think the solution might look a bit like that. Let me see if I'm right. I try and develop it. And then if it's all consistent, great. If you're more theory inclined, you can read the actual theory. in a textbook. So what we do here is we are splitting the thing in half, and then in half, and then in half, and then in half. It's a good hunch that powers of 2 are involved in here. And so why don't we say this n, let's consider n to be a power of 2. So I'll write to the side that n, I'll say it's 2 to the m for some m that is the logarithm in base 2 of n. I write log without the o when I mean in base 2. So if I do that, then this is f 2 to the m is equal 2 times f of 2 to the m minus 1 plus k 2 to the m. And I want to expand this part by using its definition and plugging it back in. So f of 2 to the m minus 1, I can use this definition, just that I use m minus 1 instead of m. So I replace m for m minus 1 every time. And so this is equal to 2 times something that I obtained by rewriting all this in here with m replaced by m minus 1. So 2f of 2 to the m minus 1 minus 1. That would be m minus 2 plus k times 2 to the m minus 1 plus the stuff that was already outside, k 2 to the m. All right. So if I do this, then I have these 2 and 2 over here become 2 to the 2 f of 2 to the m minus 2 plus this 2 over here, when I multiply it by this term, removes the minus 1 in here. So this becomes another k2 to the m, which I can add up to this other k2 to the m, which makes me 2k2 to the m. Now there's too many number 2's for me to see a clear pattern, so I'm going to do this substitution once more. If I substitute here with the exponent being m minus 2, so every time I see m in here, I replace it by m minus 2. So then this is equal to 2 to the 2. And then I expand in this way to f of, and the exponent is replaced by, so m is replaced by m minus 2, so this becomes 2 m minus 2 minus 1, m minus 3, plus inside the bracket I have k2, k times 2 to the m minus 2, plus k 2k to the m that I had from before. So at this point, these things become 2 to the 3 f of m minus 3, no, f of 2 to the m minus 3. Then when this 2 to the 2 gets into this one, it deletes this 2 again. So this again becomes k2 to the m. And added up to this one gives me 3k to the m. And so now I start to see a clearer pattern. If I did this again, it would be a 4, and the 4 would appear here and here and here. And if I did it another time, the 5 would appear here, here, and here. And so why don't I just write it out? I think this is a copy of what you had in your handout. I got to the stage of doing it with a 3. And I get to this. And if I generalize, I can say 2 to the some other letter, let's say j, 2 to the j, f, 2 to the m minus j. Plus j times k to the m. Then if I say I can keep doing that until j becomes m, and when j becomes m, then I end up here. And I don't go any further because this then becomes 2 to the 0, but this one has reached this one, which is interesting for me. And so at this point, this 2 to the 0 is 1 is a constant. So this part here becomes another constant. I don't care about f anymore. That's how I get rid of f from the right side. This 2 to the m in front is this one, plus k times m 2 to the m. So I basically have some constant times 2 to the m and some constant times m 2 to the m. Now I remember that I had set 2 to the m to be n, and so therefore m is the log base 2 of n, and so this is actually equal to n over here and n over here and n over here, and this one is log n. So I end up with some constant times n, some constant times n log n, which in the asymptotic complexity notation is theta of n log n. So I can write the cost of doing merge sort on an array of size n is theta of n log n. Cost of merge sort on an array of size n is theta of n log n. N log n. And I had proved last time that this was the optimal cost of doing merge sort. You could not do the cost of doing any comparison sort. You cannot do any comparison sort in any less than that many elementary operations, and therefore merge sort has optimal asymptotic cost, and we should just perhaps stop here and go home. Except that we were not terribly happy about the fact that merge sort was the first of the things we saw that was not capable of sorting in place, at least in the version that we practiced. We needed extra scratch space that was theta of the size of the arrays. We actually managed to use just half the size of the array, but still, that's big. Yes?
So is that proven to be an upper and lower bound?
So we proved last time that no sorting algorithm is able to do it in any less by that argument with the number of permutations that there were. Now, the fact that there exists an algorithm that does it in that much means that the best algorithm cannot be one that takes any more than that, because otherwise it's not the best, because this one does better. So what we had previously was the lower bound. What I do now with the constructive proof is giving you the upper bound. Because the lower bound and the upper bound are asymptotically the same, then this is optimal. Am I making sense? I had not proved last time what the upper bound was, but as soon as I give you an algorithm that reaches it, that reaches the same as the lower bound, then this is the best possible upper bound you can have, because anything else that uses more than that is wasteful compared to that, so it's not the best. All right. So that's all we wanted to say about merge sort. It's great, and we could consider that as the best thing we can do, except that we don't like the fact that it doesn't really sort in place. It wants extra space. So could we do better and have an algorithm that reaches the optimal asymptotic complexity but sorts in place without requiring additional workspace? And this is where I introduce you to my favorite data structure, which is the heap, because it's going to be useful in building an algorithm that has amazing features.